Oh, yeah. Hi, Mark. So we'll just give a few minutes to let folk get in. I'm glad you turned up at 12 and not at 1.
Absolutely, yes. The time zones can be a little bit different. Not
Yeah,
to mention turning the clocks forward or backwards.
yeah. Yeah, well, and I see what probably triggered the stargazing conversation as my background.
Yes, indeed.
Good.
Yeah. Yeah, last night we had gone to a local astronomy club, and a number of telescopes were set up for us to gaze at the moon, see the craters in great contrast given the crescent that was there, as well as a neat spiral galaxy and Jupiter as well.
Oh, man, lovely. It's nice when you live somewhere where the skies are clear. So
Yeah,
anyway,
there is a lot of light pollution, but fortunately, this one field was pretty reasonable, and the clouds had broken up, so it was a good night for it.
yeah, well, grand. It's nice to know a little bit of Mark that is three-dimensional and not just the numbers and the binary. So good. Well, look, let's make a start. I see we've got a number of folk who've joined us now, and others can trickle in as needed. So, just by way of introduction, I'm Roger Cressy. I am the Chief Information and Technology Officer at Association of Christian Schools International. But in this role, I am one of a group of volunteers who helps to run the AnDOUC, and I do a very small part. Mark is also a volunteer, gives very generously of his time, and our objective is to extend knowledge throughout the Oracle community in terms of the more techie side of Oracle. And Mark is joining me today to talk about data and model monitoring. The step not to skip, which I suspect many do. And he's a senior director at Oracle AI and machine learning product management. But you can really just put guru in the title there, and you'd be done. So, with that, can we step through the next slide, sir?
Certainly.
So TechCasts, this is obviously one of them. We're always looking for abstracts of interesting Oracle technological advancement that you can share with us, or cool things that you've done with your customers, or cool things as an Oracle customer that you are doing with Oracle technology. We're always interested. Please go to this site, andouc.org/techcasts, and submit an abstract. We'll review it and get you scheduled, all things being equal. Also, just to say that there is a big archive up there of very useful, in some cases, very cutting edge type presentations. So do avail yourself of it and also share what you've got with us. Next slide, sir. So there's a number of ways of getting in contact with us and of communicating inside the AnDOUC. As you can see, the website is obviously our sort of identity, as it were, but we've got Slack channels, YouTube, LinkedIn. In fact, we have a separate breakout for spatial and graph in our LinkedIn profiles. Facebook, we've even got Blue Sky now, so we're really getting trendy. And of course, X or the old Twitter. My favorite is probably the Slack. Please go along and join. You'll often get to rub shoulders with people like Mark and other product management. So it can be a good way of getting advice, especially if you're doing something that could benefit from their expertise. So with that, I think, is that my slides, Mark?
I think
Yeah.
that is.
So with that, I'll hand over to Mark. Please note there is a specific Q&A area. If you want to ask a question, put it in Q&A. Please don't put it in chat. I'll be monitoring questions and answers area, and at the end, when Mark is done and we have been saturated by his fire hose, we will then tackle any questions that have come up. Mark, of course, if you do spot a Q&A item that you'd like to deal with in flow, then help yourself. With that, I'm going to turn off my camera, and Mark, thank you very much. I'll hand off to you.
All right. Well, thank you, Roger. It's great to be here. And, before jumping into data and model monitoring, let's talk about maybe a less abstract use of monitoring from history. You may have heard of the Canary and the Coalmine. This was an early warning system for toxic gases like carbon monoxide. And that's practice started in the last decades of the 1800s. And so miners carried canaries into the mines because they were more sensitive than humans and could alert workers to potential danger. And this practice continued for over a century until electronic sensors became the standard. Now, when dealing with data and machine learning models, we also need to be alerted to potential danger in our evolving data and model quality. Now, unfortunately, many development projects focus on getting out that first release or building a suitable model, and they skip integrating monitoring of data or model quality into the solution. So as Roger said, I'm Mark Hornick with AI and Machine Learning Product Management at Oracle. And in this session, we're going to look at some of the tools available with Oracle Autonomous Database to help you with monitoring of your data and machine learning models, and also touch on data bias detection. So just to outline our agenda, we're going to start off with the machine learning process and why we should monitor in the first place. Then we'll focus on the data and model monitoring, followed by data bias detection. We'll explore concepts and examine tools available in Oracle Autonomous Database Serverless and Dedicated Region. So let's start with a scenario. Imagine that you put a machine learning model in production as part of a solution to an important business problem, maybe fraud detection. And of course, before it was deployed, the data scientists validated that the accuracy of the model exceeded business objectives. The first quarter with the solution saw significantly reduced fraud. The second quarter, however, saw a sharp uptick. Nobody knew until it significantly impacted the quarter's results. Well, what happened? Perhaps fraudsters changed tactics. The patterns that were found before the solution was deployed were no longer relevant, and in fact, they had the opposite effect. By flagging cases that weren't fraudulent and allowing others to escape detection. Of course, this wasted limited resources by having them investigate the wrong cases. If the development team had monitored the prediction accuracy more regularly, this change could have been caught much sooner, and the data scientists may have chosen to rebuild the model or select different predictors, algorithms, or hyperparameters, avoiding the surprising quarterly results. Now, similarly, if the team monitored changes in the data itself, they may have discovered problems sooner. For some data cases, you might consider an application that collects data and they've updated a pick list of values, perhaps adding, subtracting, or modifying values that the application uses. Or what was once recorded on an hourly basis is now a daily basis, or maybe the feature isn't even being collected anymore. So changes in data like these could also adversely impact machine learning model quality. And catching such changes allows taking corrective action sooner rather than later. So let's consider maybe a novice's approach to developing a machine learning solution. First, we get the data and we look at it to make sure it's what's expected, then prepare it as needed by the algorithm we chose. Of course, if we're using Oracle machine learning in database algorithms, even this step may be handled automatically. And if the results are sufficiently accurate, deploy the solution and move on to the next project. Of course, we can claim victory early, but that victory may be short-lived. And so we need to perhaps consider a more sophisticated machine learning process to get before we get to solution deployment. And this is where the cross-industry standard process for data mining, or CRISP-DM, comes in as one such process. We might start with business understanding, which involves defining the problem to be solved and the success criteria against which we'll judge the solution. And this is where executives, line of business managers, maybe data scientists and domain experts need to collaborate before moving to the next phase. Next is data understanding, which includes data exploration and visualization. And it's key to understand what data you have, where it is, what it means, and to what extent it's usable or needs to be cleaned or enhanced. And then comes data preparation, where we need to address the data quality issues we might have identified in the previous step, or combine data from multiple sources and possibly derive new variables. Now, for modeling, we need to decide which algorithms and features to use, tune those models and assess model quality, perhaps even use automated machine learning or AutoML to help with this step. The evaluation phase requires the business understanding team to assess how well the machine learning model meets the business objectives and success criteria. And this can be greatly aided by system-provided model performance metrics, model explainability, and individual prediction explainability. Now, for deployment, users, of course, need to be able to quickly and easily include model results in applications and dashboards, and need to use interfaces that mesh well with the target environment. But the step not to skip is to establish a feedback loop where changes in data and model accuracy are tracked, and models can be rebuilt as needed to reflect new data and their corresponding patterns. So, we discussed one scenario involving fraud detection to motivate the need to monitor data and models, but are there others? For data monitoring, we might consider clinical trials. In 2016, a French study on a new diet pill had to be halted after 25 participants were hospitalized with heart valve damage. Lack of safety monitoring missed the earlier signs of the side effects. In 2021, a major treadmill manufacturer recalled its treadmills due to safety issues. Earlier monitoring may have highlighted this, either at the product level or even involving customer feedback. Speaking of customer feedback, a telecommunications provider lost customers for years due to complaints about poor customer service before implementing monitoring systems to improve performance. In supply chain, the baby formula shortage in 2022 revealed that manufacturers didn't adequately monitor supplier quality and inventory. And in short, diligent monitoring provides visibility and informs course correction. Okay, so we know that data quality is important, but what about model monitoring? What are some of the things we need to consider? Well, of course, there's model performance, its accuracy and effectiveness, and this can degrade over time. As new data arrives, distributions and patterns may change, require the retraining of models. New data may reveal biases. Machine learning models are often only as unbiased as the data they're trained on. If new data contains different distributions or biases from the original training data, monitoring and bias detection can help identify possible unfairness that's creeping into the model predictions. Errors can also point to data issues. By monitoring the types of errors the model makes, data teams can spot systemic data problems. If the model consistently struggles with certain data subgroups, it may indicate issues in the data pipelines that need to be corrected, or the need to build models on perhaps separate partitions of the data. Still, in other cases, regulation and compliance may require it. In industries like banking and insurance, model monitoring is often necessary to comply with fairness, transparency, and accountability rules. And monitoring can provide some documentation in case regulators audit models. So let's look at data monitoring more closely. Data drift is a way of understanding changes in your data. What type of changes are important, though? Well, a change in the number of distinct categories in a column can have a dramatic impact. For example, consider that your application started off with a 3-star customer sentiment rating of negative, neutral, and positive, And later, the team decided to switch to a 5-star rating. Well, now 3 stars mean neutral, not positive. And suddenly, your customer rating summary metric is dropping for no apparent reason. Another type involves perhaps numeric feature distribution drift. Well, initially, we may have a normal distribution, but later it becomes bimodal, which may invalidate model assumptions. A third type can involve a drift in the distribution of categorical features. Here, perhaps our initial data was evenly distributed, but over time it became biased toward one of the labels. Now, Oracle Machine Learning on Autonomous Database Serverless and Dedicated Region provides a no-code data monitoring user interface that can help your application stay on track. It enables you to monitor changes in your data over time, called data drift. And it helps to maintain data quality standards, whether just for your data and application or in combination with machine learning. The OML data monitoring feature provides a single drift metric, allowing you to easily track overall data drift. And it also provides statistics on individual features and their interactions. So you access the no-code data monitor interface by clicking on the data monitor's quick action or by accessing it through the menu. But let's visualize the process for data monitoring. We start with our baseline data and then provide new data in subsequent periods to be analyzed. And we can specify a threshold above which we might consider the data drift metric should alert us to changes. Where to place this threshold, of course, is problem specific, and it may need to be adjusted over time. Now, in a sense, we can think of this as our proverbial canary in the coal mine. The data set that we're going to use for the demo involves individual household electric power consumption. So let's briefly introduce that. We have temporal measures indicating the date and time of each measurement, of course. There's the specific area electricity measurements, for example, that indicate readings from maybe the kitchen, the laundry, or water heater and air conditioning units. But the main power measurements consist of the items called global active and reactive power, voltage, and global intensity. Now, global active power is the power that does the real work, like heating your water or running your refrigerator. Think of this as the electricity that you're actively using. The global reactive power is considered maybe the behind-the-scenes power that helps run your appliances smoothly, but doesn't directly power them. Voltage is like water pressure in pipes. Fluctuations in voltage can affect how appliances perform, and global intensity measured in amps is like how much water is actually flowing through the pipe. Now, how do we use this data then? Well, we're going to be specifying our baseline data table, which in our case largely covers the winter months of 2007. And we have a single new table that contains data from 2008 to 2010. And we'll be doing monthly comparisons, so different monthly subsets of data will be used. And next, the monitor will compute metrics on the baseline data set, and then compare this with each new data subset. So let's see a quick demonstration of the interface. Now, this is the main user interface to Oracle Machine Learning on Autonomous Database. And we're going to go into the data monitors. And I have one built here. It's an AND power consumption data monitor. We can see the settings that were used. This is our household power base, baseline data that we used. And the new data is houseline power new. We're going to use a crosstab column to understand relationships between global active power and all of the other columns in our data set. The dates column is our time that we're going to be using for the interval, and our analysis period is on a monthly basis. And there are a few other settings as well, like the drift threshold, which is set by default at 0.7, which we can adjust. And of course, the database service level set to medium to give us some parallelization there. Now, of course, our original data was from 2007. We're up to 2010, and we're seeing that, yes, the data drift is a bit higher, and even in the August timeframe, it went further than that. If we look at the individual features, we can see their relative importance and how that's changed over time, the percent missing, and other statistics that are available. But let's click on global active power. Now, there are a number of metrics that you can look at, like population stability index, Jensen-Shannon distance, and others. And these are all defined with various formulas in the product documentation. But here we see that there's a significant difference from the, say, winter months versus the summer months. And it certainly is identifying various changes over time. Summary statistics are also available for the set of time periods that you may want to look at. You can select the exact time periods of interest. And then there's also the distribution for the values of this particular column. And here we see from the baseline that we've had an increase in this lower section of the values for this particular column. And we don't have a crosstab column here because this is the column that we selected for crosstab. So let's go back to checking, maybe comparing this with voltage. And here we see other metrics as well that we can work with, and the distribution with the crosstab column itself. So we have global active power with voltage, and it's highlighting that this particular combination has the most values associated with that. All right, so that gives you a quick view of some of the metrics and capabilities that you have with the data monitor. Now, as part of OML services on Autonomous Database, you also have programmatic access to data monitoring using REST APIs. Here's an example using curl for data monitoring. We first get an access token, then create an asynchronous job, and then we can view the job details and then view the results stored in the corresponding table. So let's move on to model monitoring. Some of the factors that can contribute to model drift are shown here. One is concept drift, where the properties of the target variable, what we're trying to predict, actually change. The fraud model could have concept drift, where the classification of what is fraudulent changes. Data drift is where the properties of the predictor variables change. Examples include changes in data due to seasonality, changes in consumer preferences, and the addition of new products. Or, as we've noted earlier, changes in fraud tactics. Now, upstream data changes refer to operational changes in the data pipeline. And this occurs, for example, when a feature is no longer being generated, perhaps resulting in missing values. Or there could also be a change in measurement units, such as a distance changing from miles to kilometers. That could have a dramatic impact on how those values are interpreted. Now, we talked about data drift already, so let's focus on concept drift. This is where changing patterns in the data make the machine learning model less accurate. As we see on the left, the original data has a boundary that does a reasonable job of separating the two classes when making predictions. However, with concept drift, we see that some of the triangles no longer respect this boundary. And if we were to rebuild the model, we might expect a new boundary to be established. Now, like data monitoring, OML also supports a no-code model monitoring UI for tracking model quality over time. Also, like data monitoring, you can track overall model drift using a single drift metric. And again, insight into how changes into predictors impact those model predictions. Model drift is the percentage change in the performance metric between the baseline period and the new period. Positive value indicates that the new period was not as good, while negative value indicates that the new period actually did better, which is perhaps often unexpected. These metrics can help guide the decision of when it's necessary to rebuild your model. To visualize the process for model monitoring, again, we start with our baseline data and one or more classification or regression models, and then we provide new data. So over time, different models may perform better than others on new data versus the baseline data. Higher values, closer to 1, mean that you can tell the difference between how well the model performed on the baseline data versus each of the new data periods. And we can specify a threshold above which we want to consider this metric. As for data monitoring, where do we place the threshold? Well, this is also problem specific and may be adjusted over time as you gain experience with the results. Note that we're going to be using the same data as we did for data monitoring, and we'll provide regression models to predict global active power. So as before, you access the no-code model monitor interface by clicking on the model monitor's quick action, or you can access it through the menu. All right, so let's see a quick demonstration of this interface. So we're going to go into model monitors, but first it will be useful to say, how did we get the models that we wanted to monitor? So one of the tools that we have in Oracle Machine Learning on Autonomous Database is the AutoML user interface. And you see we have an experiment AND power consumption. The settings that we chose for this, of course, were to use the household power base. We have a model metric of mean squared error. We're trying to predict global active power. It's going to be a regression problem since we're predicting a numeric value. And we can see the set of models that were produced. 5 in all were produced, and 3 of these we've decided to rename to make them easier to identify. Here we've got AND power neural network, GLM, and support vector machine linear. Of course, you see the various metrics that were computed for each of these models, so you have a quick view of things like the mean squared error, the R squared, and others. Now, in order to make these models available for the model monitoring UI, we need to deploy them to OML services. And this can be done very simply by clicking the deploy button here and specifying the URI we want, the version, namespace, and whether or not we want to share those. But we've already done that. So I'm going to move over to our models interface. And here you can see all of the models that are available. And if we look to power, these are the models that we built from this experiment. And if we go to deployments, you see these are the models that we deployed: GLM, neural network, and support vector machine linear. The namespace we assigned them. And if we click on one of these, of course, you'll see the model metadata for that, as well as the OpenAPI specification for this particular model. So we could use this from REST endpoints to do real-time scoring, for example. Now, of course, we deployed these by using the AutoML user interface, but we could also have deployed it from here, selecting any of the models that we have available to us, and then saying deploy, and that would provide us with that same interface. So with this as a foundation, let's go to our model monitors. And here we have also AND power consumption model monitor. The baseline data, of course, is the same that we had when we were looking at the data monitoring. We have household power new for the new data. We're going to be monitoring this perhaps on a weekly basis. And we see the metric we're going to keep as mean squared error. And the database level, again, is medium to achieve some parallelism in the underlying processing. Now, these are the models that we've selected to monitor, and you can see the model drift metrics over time for the periods illustrated here. And at one point, the support vector machine linear model surpassed the 0 level, indicating that it has significantly deviated from the original data set that was used when testing the model. You can also look at the metrics that are reported for these over time, and we see they're fairly consistent. Although when you look at mean squared error, the absolute error, and median absolute error, there are some deviations. Certainly the GLM model is significantly different than the others. There are also prediction statistics that you can look at as well to assess how the models might be different. But let's take a look at a specific model here. We'll look at GLM, and we get some additional information on the model itself. Feature impact. Which are the features that are most impactful on the predicting the target? And so we see global intensity is very high here. All of the others are paling in comparison. But if we take a log scale, we can get a little more visibility into that. And we can see how the various features here, we're limiting it to the top 5, are contributing to the model's predictions. For the time periods selected here, of which, again, we could select other time periods, we can have the prediction distribution. So we see against the baseline how the more recent data segments are having their predictions distributed differently. So here we're seeing more of the smaller value predictions, whereas in the higher value ranges, we're seeing less for the most recent, say, the November period. One other piece of information that is available is also this predictive impact versus drift importance. And so here we can get a sense of how impactful the given feature is, predictive feature impact, against the drift feature importance. How significant when it drifts its values, is that going to influence the outcome? So here, of course, we see the global intensity as being the most predictive feature impact, but also a significant drift feature importance. Whereas here, submetering 3 contributed perhaps most to the drift feature importance, but has less predictive feature impact. Now, OML Surfaces also gives you programmatic access to the model monitoring using a REST API. And like data monitoring, we get an access token, create an asynchronous job, view the job status details, and then we can view the results using a SQL query. So next, let's touch on data bias detection. One recent feature that we've added to OML services is the data bias detector, which can identify, possible bias in data that can impact model quality. It's accessible through the REST API, and data bias, of course, can lead to machine learning models that are at best less accurate, but perhaps more importantly, unfair or even harmful. You might imagine, a healthcare scenario in which the model predicts how a patient may respond to a particular treatment or drug. An underrepresented subgroup of patients may be predicted to respond well, when in fact, this is more representative of the larger population, not the subgroup. And it could, in fact, be harmful to the subgroup. So proactively addressing data bias certainly has multiple benefits. Companies concerned with regulatory compliance, know that models are under increased scrutiny and regulation. So detecting and mitigating bias can help address such requirements. Understanding bias can lead to more accurate and reliable models for better decision-making and better customer experiences. It's also important to note that bias can result from multiple factors, including how that data is selected, measured, or labeled. Just a few examples: selection bias can result from sampling data in a way that doesn't represent the overall population. or survivorship bias, which focuses on cases with successful outcomes, but ignores, or the data isn't available, regarding failures. Or coverage bias, where for whatever reason your data collection method omits important population segments. And the data bias detector supports several bias metrics that can help in this area. So let's take a look at some of those. First is, class imbalance, which occurs when you have too many examples of one type of entity and too few of others. But you're trying to predict all of them with similar accuracy. Models are less likely to accurately classify underrepresented entities. Some of the metrics are like statistical parity. This involves evaluating whether the distribution of positive predicted outcomes matches the distribution of underlying groups. And think about hiring or loan approvals. Statistical parity means that people hired or had their loan approved within specific groups, perhaps based on maybe gender or ethnicity, are proportional to their representation in the larger population. And then there's conditional demographic disparity, which helps you identify hidden biases and assess fairness across different groups within a larger group. Let's take a little closer look at CDD. Now, CDD can help identify when your data may suffer from what's called Simpson's paradox, where a trend appears in several groups of data, but disappears or reverses when the groups are combined. Take the UC Berkeley gender bias case from 1973. Initially, women applicants appeared to have a lower acceptance rate, but looking at individual departments, no bias was actually found. The overall bias was due to women applying to more competitive departments with generally lower acceptance rates. And similarly, when looking at smoking or mortality rates among British doctors, initial data analysis showed non-smokers had a higher mortality rate. But this was because non-smokers tended to live longer, and older people have higher mortality rates regardless of their smoking status. So through OML services, you also have programmatic access to the data bias detector using a REST API. And as before, we get an access token, we create a job and view the job's status details, and finally view the results from the table that's provided. So to wrap up our discussion of monitoring and bias detection, our objective is to enable taking informed action and mitigate harmful outcomes. We need to be able to detect changes in performance quickly, identify likely causes and solutions, which can include addressing data issues, rebuilding models, or changing the entire machine learning methodology. And the OML features that we've just discussed can help. Now, this table provides a summary of the OML components and where they're available across Oracle Database and Autonomous Database. On Autonomous Database Serverless and Dedicated Region, OML provides the no-code user interfaces for data and model monitoring, and OML Services provides REST endpoints for data and model monitoring, as well as data bias detection. Of course, you have access to our APIs for SQL, Python, and R, as well as the built-in notebook environment and the AutoML UI in Autonomous Database, and even our original UI Oracle Data Miner, which allows you to connect to various Oracle databases as well. So for more information on Oracle Machine Learning and to get started using OML, check out these resources. If you want to try Oracle Machine Learning on Autonomous Database, we have Oracle Live Labs workshops. One of the links here is for OML Fundamentals, which covers several of the components that we've discussed. And so with that, thanks for learning about Oracle Machine Learning. Roger, back to you.
Well, thanks very much, Mark. We have it's really a question that someone has answered, and there's clarification needed. But Ram Iyer says we encounter numerous types of data models with which underlying data model functions most effectively with an ML model. And just so people are then discussing reactive power as well. But if that, let's answer that one first, maybe.
Well, okay, so if multiple types of data models and which underlying data model functions most effectively with an ML model, I think that you have to think about how do you prepare data for modeling in the first place, right? I mean, if you have a star schema, uh, your typical machine learning algorithms, certainly the ones that we have in the Oracle database, they require you to have one row per case, typically. And so what that means is that you will need to flatten out that data. If you have a star schema, you'll need to decide which are the features that you want to have included when building a model, if it's predictive for classification or regression, or even if you're trying to do clustering for that. That's a case where you need to prepare the data properly to allow the algorithm to work correctly. However, that said, there is this notion with the Oracle database and Oracle machine learning in particular, where we have nested data. And nested data allows us to deal with sparse data. And so you can have a column then that contains a nested column, and many of the algorithms are able to work with that at the SQL level if you're using the PL/SQL API for building models. And so that can give you a little bit more flexibility for that. Otherwise, you can define views or materialized tables on the various joins between the tables you're working with to provide them to the machine learning algorithms.
Very good. I think the other is sort of more of a discussion rather than questions, I see. uh, yeah. Mark, thank you. As always, I love the practical examples you give that highlight some of the issues that we face with things starting to fall off track. And this is a very practical bit of knowledge that you've given us today. With that, I don't see any more questions for now, and all that remains really is for me to say thank you. Again, just to remind people to submit TechCast abstracts and join us on the social media that we have available for you. These are obviously some interesting links. And this will all be available for you. This recording will be saved both to our website and to YouTube within a few days, depending on Wayne's availability to get it done for us. So with that, thank you so much again, Mark. Appreciate it. We look forward to the next TechCast. Yeah, May 29th. We've got Jim Saprinsky giving us, he's always a good storyteller. In fact, that's his email, in fact, is even about being a storyteller. So, thwart toil through tiles, leveraging Oracle's 23A's latest geospatial features. So, we look forward to seeing you then. And in the meantime, thank you, Mark, once again.
My pleasure. Thanks for having me.
All right. Bye-bye.